So unlike what it says on the program, I'm actually a postdoc at Space Telescope. I'm not at UC Santa Cruz, at least as far as I know. And I wanted to tell you today about close pairs as probes of dark matter accretion and star formation. But before I do, I'll just give you a couple of slides of advertisement for work that I did with Joe Silk earlier this year about predicting very high redshift star formation and galaxy evolution from looking at galaxy-specific star formation rates and their halos-specific mass accretion rates to guess at how they would evolve on the stellar mass-halo mass plane. And using this technique, we can estimate how the cosmic star formation rates evolve to very high redshifts, how the stellar mass-halo mass relationship evolves, specific star formation rates, and even make predictions for James Webb, what it will see in terms of the stellar mass function. And unlike other studies, we actually do include error bars at these very high redshifts. So our results are falsifiable. OK, anyway, so moving on to the real talk, just to give you some context, in a paper last year, I suggested that the star formation efficiency in halos between redshift 0 and redshift 4 is almost completely a function of halo mass and not at all of time. And so this plot is showing you what I mean by efficiency, which is the average star formation rate in halos divided by the average baryonic accretion rate within the virial radius. And as you can see here, there's a peak right around 10 to the 12 solar masses, or a little bit less, which is fairly independent of time. But then there's 5 orders of magnitude of difference in the halo mass direction. And so, as Eric might say, I was very smug after doing this because I think, well, here's how halos turn gas into stars. But then along came these guys, Andrew Hearn and Doug Watson, and with this age matching model, which does an extremely good job of matching in Sloan the quenched and star forming on top. There are the correlation functions on bottom, the stacked weak cleansing signals. They also looked at the quenched profile of galaxies around groups and clusters, and that all matches well. And the very puzzling thing about age matching is that what do they use as the halo proxy for whether a galaxy is quenched or star forming? So in a couple of senses, all age matching is this abundance matching of galaxies to halos to get stellar masses. And then to decide whether something is quenched or star forming, you use a proxy of the halo age and say that older halos, in other words, earlier assembling halos, are the ones that have quenched galaxies. The younger ones have star-forming galaxies. But the effective age proxy which they used was the 4% mass assembly time of the halos. And here I'm just plotting for you, say, L-star centrals. What's the range of 4% assembly time redshifts, basically, which is between 3 and 5. And this has almost nothing to do with the recent accretion. So if you look at recent major mergers, I've plotted the same, I guess, distribution. And you can see that they're quite overlapping. And so according to their model, or at least if you believe that their model is describing the real universe, the recent accretion doesn't actually matter for whether something is quenched or not. It's more related to the early formation history of the halo. So this was extremely puzzling to me. And I thought it might be actually possible to tell from observations whether this is true or not. Does quenching depend on recent halo accretion at all? OK, so here's the idea. If you look at the mass accretion history of a halo, when does it have the most mass accretion? Well, it has that in major mergers. And major mergers for halos look like close pairs of galaxies. So if you do your close pair selection properly, you can preferentially select major mergers, and so preferentially select galaxies whose host halos have had large recent accretion onto the halos. Now, you might ask, why am I doing another close pair study when there's about 1 for every astronomer? I guess I have to fulfill my quota. But there are a lot of biases which can really screw you up when you're talking about close pairs. So here's one of them, which is if you think about the stellar mass-halo mass relationship, most people define close pairs or a paired galaxy as a galaxy which is maybe, say, 0.5 dex or 1 dex less than the larger of the two galaxies in the pair. And what that means in terms of the halo mass is very different depending on which scale you're talking about. So more massive things, the stellar mass-halo mass relationship turns over, and so 1 dex in stellar mass is a huge range in halo mass. And so massive halos have a large number of satellites which are close to the mass of the central galaxy, whereas small halos in small galaxies do not. And so if you select close pairs based on this, the very fact that you have a satellite which qualifies as a close pair is going to bias your halo mass in your selection. And so in fact, biases of this type are so useful at determining the halo mass that people have used, say, the existence of the LMC and SMC to constrain the mass of the Milky Way. So it's important to consider this. And so what I ended up doing is, in a very narrow mass range, you're roughly OK, right around 10 to the 10 to 10 and a half, so that a constant ratio in stellar mass translates to a constant ratio in halo mass, and you're not biasing yourself so badly. OK, so make a long story short, selection for host galaxies, I'm looking at slightly sub-L-star galaxies, 10 to the 10 to 10 to the 10 and a half solar masses. And because I want to study star formation in centrals, I want no larger galaxy within 500 kpc. And here's actually another thing which can bite you. So I'm using Sloan spectroscopic data. But if you look at the spectroscopic sample, like these red squares tell you where all the spectroscopic targets are, there's a bias in Sloan against selecting BCGs for spectroscopic targets, which I'm happy to talk to you about later. And so if you don't actually visually examine all these close pairs, then you can get situations where this one and this one would qualify as a close pair, but when in fact there's this big honking BCG sitting right next to you. So anyway, so I had to look through all the galaxy pairs. So my selection criteria for the smaller of the two, so I called something a paired galaxy if it's within half a dex smaller in stellar mass than the larger of the two, and within 500 kilometers a second in redshift. And I call it a close pair, because eventually I'll look at things as a function of distance to the paired galaxy. I call it a close pair if it's within 200 kpc of the larger galaxy. OK, and so here's just a photo montage of the 10 closest pairs in Sloan that pass all my selection criteria. These are 40 by 40 kpc tiles, so you can see all these things nicely. And if you're familiar with looking at quenched and star-forming galaxies, you can probably already guess the punchline, or one of the punchlines of this talk. But at least bear with me for the moment. In order to get halo masses and halo accretion rates, we obviously can't go and look at tags in Sloan. We have to go to Mach catalogs. And so I build Mach catalogs using abundance matching, taking the same stellar mass function for the galaxies I'm using in Sloan. And you don't have to read all these plots separately, but the point is that the abundance matched Mach catalogs do an excellent job of matching the kinematics, the large-scale environment, and the radial distribution of the close pairs for the observational galaxies. And key point, that the halo masses that I get from my close pairs are extremely similar to that of the whole sample. So if I have a close pair or if I don't, the halo masses are extremely similar, but the accretion rates are extremely different. So these accretion rates, if I'm averaging over the past 5 gigayears, which is about to redshift 0.5, my accretion rates are double in terms of the median, the mode, the average, everything compared to things without a close pair. OK, and actually, if you look at the stacked accretion histories, this black line is the average for all galaxies in my host sample, and these colored lines are the averages for the things with close pairs. And you can really see just a huge increase corresponding to major mergers happening within the past 5 gigayears. And you can do other fun things with the Machs, like ask, where do you have to draw your selection point for close pairs such that you have the largest increase in accretions, blah, blah, blah. OK, so results. As I said earlier, you could probably guess my results just by looking at this picture. And I'll helpfully label for you the galaxies, where the tiles where the host galaxies are quenched. There. So 5 out of the 10 are actually quenched, even for these very close pairs. And if you're familiar with the quench fraction for galaxies in Sloan in this mass range, you'll know that actually about 50% are quenched regardless of whether they have a close pair or not. So this is 10 galaxies. Let's throw 430 galaxies in a plot, and it looks like this. So this is a specific star formation rate distribution, specific star formation rate down here at quenched, star forming. Black line is all the host galaxies in my sample. The colored lines are the ones with close pairs, and I cannot see a strong increase in the star formation rate or the quench fraction, sorry, the star forming fraction for the close pairs. But that's not to say that there aren't certain subsamples of galaxies for which an enhancement exists. So for instance, if I look at the star-forming fraction, maybe there's some evidence at very close distances within 30 kpc for an increase. If I look at the star formation rate as a function of the distance from the nearest close pair, and remember I define close pairs as being within 200 kpc, I see maybe a little bit of a bump here, not too significant. Maybe a bit of a bump here for very close pairs. Again, not that significant. I mean, for sure, nothing on the same order of magnitude as the factor of 2 increase in the halo accretion rates. But maybe a little something. And then it gets a little bit clearer if I then split by star-forming hosts and quenched hosts. So I caution that these results are cool. I don't completely understand them yet. But they're interesting because for star-forming hosts, I can see definitely for sure an enhancement around 150 kpc and a big enhancement for things within about 30 kpc. So my naive interpretation of this is that the virial radius for the host galaxies are 200 to 300 kpc. And so maybe there's an enhancement either just when things come into the virial radius, or as Jen pointed out to me yesterday, when things come in, pass through, thank you, and then are on their first passage out. That could also be these. I can't distinguish with the data, of course. And then you have something very close in, perhaps when the cold gas reservoirs are merging, you have an increase in the star formation rate. And if you look at the quenched hosts, perhaps by definition, there's no enhancement in the quenched host star formation rate. But what's interesting is down here, when you get to very close pairs, and maybe what this is that you're just dragging the quenched galaxies which are just barely quenched and putting them in the star-forming sample and leaving only the most strongly quenched galaxies as quenched with these close pairs. Okay, so I'll just put up the summary. No major star formation enhancement, at least not on the level of the increase in the halo accretion rates, which I would expect for the hosts. But there's some interesting features like this double peak enhancement for star-forming galaxies, which I think will require more interpretation. So, thank you.
Thank you, Peter. Impressively, everybody has been so well behaved. We have lots of time for discussions and questions to Peter first. Robert.
You see, some of the things are there, partner.
Mm-hmm. Mm-hmm.
That both pairs or the digit pricing fraction is just much larger there. My question was, so this is of course your local polar universe. What is the feeling of what it is?
Yeah, so I hope that as you go to higher and higher redshifts, that star formation is more correlated with the recent accretion rate, because otherwise everything that we've learned from simulations is wrong. But at least my intuition is that the recent accretion rate should be more relevant at high redshift. Yeah.
So you happen to choose 10 to 10.5.
Yeah.
I would thought that's so close to where the halo might actually be close to quenching anyway.
Yeah.
And therefore, you happen to choose a regime which could be confusing. Whereas in fact, you chose, say, smaller.
Yeah.
You might have gone to better.
And in fact, yeah, so in fact, it's really related to the biases that I was trying to avoid, because in order to avoid this bias of halo mass, I had to choose a region where it was basically flat in terms of the stellar mass-halo mass ratio, which is then where quenching starts to become important. So I had to choose a confusing region to avoid some of the biases, which would make it confusing for other reasons. So,
it might be interesting
yeah.
just to see whether
Yeah.
your expected biases really pan out, right?
Yeah.
Biases are also preconceived ideas of what
Sure.
Are your star formation rate corrected for dust?
So these are from the MPA GHU catalog, and I am told that they include dust corrections, but of course, you're welcome to believe in different ones.
If you
Yeah.
You can just pre-compensate for that and say, I want a 1 to 3 like table merger, so I'm going to look at a 1 to 5 or 1 to 2, whatever.
Yeah, so you can do something a little bit more clever in the sense that you can also have your close pair threshold be depending on the stellar mass of the host, for instance. So that would help. Or you could have like the distance within which you call something a close pair depend on that. And that might also help.
Just a quick one. First in Z-Cosmos, redshift to 0.5, we found much smaller samples, very small enhancement only at the closest separation.
Yeah.
30 PVC.
Yeah.
We assumed that that was again just sort of kicking the existing.
Yeah.
The thing I was going to ask again sort of echoes a little bit what David was saying. These are, more or less equal mass molecules.
Yeah.
So at the mass you are, touching on the point I was making earlier today, at the mass you are, the halo which has come in has also been pretty efficient at making gas into stars.
Yeah.
Whereas perhaps one would be thinking of much lower, the accretion of much lower mass
Yeah.
halos as what would be perhaps fueling the sort of steady state star formation.
Yeah.
And so I just wonder what happens if you look at a much bigger mass range.
Yeah. Well, since we're both theorists, I can be a little bit more quantitative. So here's the peak, which is at 10 to 11 and a half. And if I go to the earliest slide, here, I mean, if I look at 10 to the 11 and a half, these things actually still have to be quite efficient at forming stars. And so even though I agree with you that this is where the quenching is starting to kick in, it's not for sure that, yeah. 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 Yeah.
Then you want a measure of the accretion rate of halos down well below 10 to the 11.
Yeah. It's fair.
You talked about stellar halo relation where it's flat, such that you can
Yeah.
referring to Eric's talk, is at 10 to the 12 halo mass, that's where we have the most diverse population in galaxies.
Mhm.
We have red and blue galaxies.
Yeah.
So I wonder whether this leads to an additional bias on light. It's hard to account.
Yeah, so I think what we can say for sure is that star-forming hosts do different things from quenched hosts, and that if you average them together, you're really muddling the picture. But I think you can also answer the question which I posed originally. Does the quenchedness of a galaxy correlate with its recent halo accretion? And I think even the stack, even though it's muddling the picture, tells you that probably recent accretion isn't as important as you might have guessed beforehand. What's that? Okay.